Okay, let's dive into the ultimate fate for most stars out there. Not the big supernova banks, for most of them anyway, including our sun.
Right.
Instead, it's more of a quiet fade. They shrink down into these incredibly dense, really tiny things called white dwarfs.
That's it exactly. I mean, think about taking something like the sun's mass, which, volume-wise is like a million Earths, and squishing it
Wow.
down to something basically the size of the Earth. The stuff inside is packed so tight, the electrons get forced into this state called degeneracy.
Ah, right, that quantum thing.
Yeah, it's a quantum mechanical state. Basically, electrons really don't like being squished together any further. They push back.
And that pushback, that degeneracy, that's where one of the most fundamental ideas about these stars comes from, right? The mass-radius relation.
Precisely, yeah. It's a prediction that comes straight from the physics of that fully degenerate electron gas. It basically says, okay, for this much mass, the white dwarf should be this big.
And people figured this out quite a while ago.
Oh, yeah. Pioneers like Chandrasekhar worked this out way back in the 1930s. And it got refined later by people like Hamada and Salpeter. It's really a cornerstone for understanding white dwarfs.
And it's not just like a theoretical curiosity. This mass radius thing is actually crucial for a lot of astrophysics.
Absolutely vital. If you want to figure out how massive a white dwarf is, you often lean on this relationship. It pops up everywhere.
Like using them to measure distances?
Yeah.
Or figuring out how old stars are?
Exactly that. Calibrating cosmic distances, dating star populations by how fast the white dwarfs are cooling down, which tells you their age, essentially.
Hmm.
It even helps, put limits on fundamental constants in physics.
Okay, so it's super important. But you note here that despite all that, this relation was basically just theory for decades.
Yeah, that's what the sources emphasize. It remained largely a theoretical construct, even though white dwarfs are everywhere.
That seems kind of wild. How could something so central be so hard to actually check against real stars?
Well, the core problem is you need really good measurements of both the mass and the radius for the same white dwarf. Getting
Oh.
both accurately. That's tricky. And to make it harder, most white dwarfs we see tend to have masses clumped together around 0.58 times the sun's mass.
So you don't get a good spread of data points to see if the whole theoretical curve holds up.
Exactly. It makes it tough to really map out the relationship across a wide range of masses.
Got it. So, okay, before we had the really amazing tools we have now, what did astronomers do? They must have tried something, right? Had to get creative.
Oh, absolutely. They had some clever approaches. One common one was looking really closely at the light from the white dwarf surface. Spectroscopy.
Analyzing the light?
Yeah.
Hmm.
You compare the spectrum you observe to these theoretical model atmospheres, basically, detailed simulations of what the light should look like coming from the star's outer layers.
And that tells you temperature, gravity.
Temperature and surface gravity, yeah, how
Mhm.
strong gravity is right at the surface. And if you know the surface gravity, and you have some idea of the radius, maybe from the temperature, and how far away you think it is, then you could sort of work backwards.
Using the theory again.
Right. Using the theoretical mass-radius relation to estimate the mass. But you see the problem.
Yeah, it's a bit circular. You're kind of assuming the theory is right to test the theory.
Exactly. It relies heavily on those models being correct and getting the distance right. So not ideal for a clean test of the relation itself.
Okay, so that was one way. What else?
Another neat trick involved using the star's own gravity. White dwarfs have incredibly strong gravity, and that actually stretches the light waves coming off them.
Ah, gravitational redshift.
That's the one. It's just the light towards the red end of the spectrum. It's different from Doppler shift, which is about motion.
Right, motion towards or away from us. This
Yeah.
is purely gravity bending space-time.
Yep. So if you could measure that gravitational redshift really accurately, you could figure out the surface gravity again.
And from surface gravity, you can get mass and radius.
Sometimes. Yeah. Potentially independent of distance. But the huge challenge there was separating that tiny gravitational redshift from the much bigger Doppler shift caused by the star just moving through the galaxy.
Ah, okay. Tricky.
Very. It worked best for white dwarfs that were, say, in binary systems or star clusters where you had a better handle on their overall motion.
Speaking of binaries, that was another method too, wasn't it? Using orbits.
Yes, exactly. If you have a white dwarf orbiting another star, and you can actually see both stars, a visual binary.
Okay.
And crucially, if you know how far away the system is using parallax.
Parallax.
Yeah.
That's the apparent wobble as Earth orbits the sun, tells us distance.
The very same, our fundamental yardstick. So if you have the orbit measured precisely, and you have the parallax distance, You can use good old Kepler's laws
You get the
to
mass.
get the mass of each star in the binary. Then you could try to measure the white dwarf's radius separately, maybe from its brightness and temperature, and boom, you have an independent mass and radius pair to check against the theory.
So we had spectroscopy, gravitational redshift, binaries. Quite a toolkit, but still you're saying they couldn't definitively confirm the mass-radius relation.
Not really nail it down across the board now.
Hmm.
Even when they started getting better parallax measurements from the ground for nearby white dwarfs, the measurements just weren't precise enough.
Too much scatter in the data.
Yeah, the errors on the mass and radius were just too big to clearly see if the data followed that specific theoretical curve, especially away from that common 0.58 solar mass clump.
Then came the Hipparcos satellite, right? Better parallaxes from space. Did that
Dude,
solve it?
Hipparcos was definitely a big step up, much better precision.
Yeah.
But it only observed about, 22 white dwarfs?
Yeah.
And a lot of those were right at the edge of what it could reliably detect.
So still not a huge sample.
No. And while the data was better, and studies using it showed the mass and radius points clustering much more tightly.
Consistent with the theory.
Mostly consistent with the standard models, yeah. The ones assuming the white dwarfs have cores made of carbon and oxygen, CO cores, with maybe a thin layer of hydrogen on top, that's the standard expectation.
But it still wasn't like a slam dunk confirmation of the shape of the curve over all masses.
Not quite. The sample was small, and crucially, it didn't have many examples at the really high or really low mass ends. That's where the curve is most distinctive, where you could really test the theory rigorously.
And different stars could end up as white dwarfs with different stuff inside, right?
Yeah.
Complicating things.
Exactly. Plus, even for really famous, well-studied white dwarfs and binaries, like Sirius B, or Procyon B, the details were still a bit murky. Uncertainties remained.
And didn't some of those earlier studies hint at things being even weirder?
Oh, yeah. That's where it gets really interesting. There were some analyses, like one by Provençal and colleagues back in '98 using Hipparcos data, that suggested a few white dwarfs seemed too small.
Too small for their mass, according to the standard CO core models.
Exactly. Their measured mass and radius seemed to fit better with theoretical models for white dwarfs made of iron.
Iron cores.
Yeah, including maybe Procyon B. And even before that, there had been some more speculative discussions about potentially even more exotic things, like strange dwarfs made of quark matter, super dense.
Okay, quark matter is definitely out there. So before the next big thing, the picture was sort of general agreement for the common white dwarfs. But testing the precise relation was tough, and there were these intriguing hints of oddballs.
That sums it up pretty well. And it's really worth stressing something the sources point out. Before the Gaia mission, there hadn't been a single, clean, empirical test of the mass-radius relation for an individual, isolated white dwarf.
Not one. They were all indirect or needed binary systems.
Correct. Nothing truly definitive for a lone white dwarf.
Which finally brings us to Gaia, the European Space Agency mission, the game changer.
Absolutely. Gaia has just revolutionized astrometry measuring star positions, motions, and distances. Its second data release, DR2, was phenomenal.
How many white dwarfs are we talking about?
Well, DR2 identified something like 260,000 white dwarf candidates across the sky. And get this, over 8,000 of them were within about 326 light years, just 100 parsecs.
Whoa, that's a lot more than 22.
It's an absolutely massive leap in both the number of stars and the precision of the distance measurements, the parallax. Unprecedented.
And that level of precision that finally opened the door to doing those really solid empirical tests.
Yes. Exactly. And one really stunning example, a specific result they highlight, involved a single isolated white dwarf named LRWD-37.
Okay, LRWD-37. What was special about it?
Gaia's incredibly precise measurements of its position over time, combined with some follow-up observations using the Hubble Space Telescope, allowed astronomers to measure its mass in a really cool, rare way, astrometric microlensing.
Microlensing, wait, that's when gravity bends light, right, like a lens.
Yep. But here, they weren't looking for a background star getting brighter. In astrometric microlensing, you watch the foreground star, the white dwarf, LWD-37, appear to shift position ever so slightly.
Why would it shift?
Because its gravity briefly bends and magnifies the light from a background star that happens to pass almost directly behind it, from our point of view. That bending makes the white dwarf itself seem to wobble a tiny bit.
That sounds incredibly difficult to measure, like impossibly small shifts.
It is, utterly tiny. But the combined power of Gaia and Hubble made it possible for LWD-37. And the mass they calculated from that microlensing event.
Yeah.
About 0.56 times the mass of the sun. And it lined up beautifully with the mass predicted for that white dwarf, using the standard theoretical mass-radius relation and theoretical cooling models.
Wow.
Those cooling models predict how a white dwarf's temperature and brightness should change as it cools over billions of years. So getting agreement from this independent lensing-based mass was huge.
So that was it, the first empirical test for a single isolated white dwarf.
That was it, a real landmark, just confirming the theory for one lone star in such a direct way.
That's amazing. Okay, so that's one star. But with Gaia's huge numbers, they could then test the relation more broadly, right? Across thousands of stars.
Exactly. People jumped on the Gaia data pretty quickly. There was an early study using the first data release, DR1, that showed good general agreement, but there were still some uncertainties, like in the atmospheric properties, that limited the precision a bit.
Okay, but then DR2 came out with even better data.
And that's when things really clicked into place. Several studies using the much-improved DR2 parallaxes delivered incredibly strong empirical support for the whole theoretical mass-radius relation.
Which ones?
Well, there was one by Bedard and colleagues in 2017. They looked at over 200 white dwarfs with good Gaia data. And they found that, get this, 73% of them were consistent with the standard CO core models within the measurement errors.
73%. So for the vast majority, Gaia just nailed it. The theory holds up.
It really does. It's powerful evidence that electron degeneracy pressure is doing what theory says it should be doing inside these stars. Now, they did flag some outliers. Some turned out to probably be binary systems where you had two white dwarfs orbiting each other, but Gaia saw them as one star initially unresolved double degenerates.
Okay, that makes sense.
But they also spotted a few others that, based on the estimated mass and radius, seemed to fit better with those iron core models we talked about earlier, echoes of those hints from the Hipparcos days.
Really? So the iron core idea came back?
It did, initially. One star in particular, called G8777, looked like a pretty compelling candidate for maybe having an iron core based on that early DR2 analysis.
Huh. So the mystery wasn't quite solved.
Well, hold on. Science marches on.
Uh,
A later study, this one by Bergeron and collaborators in 2019, used the final, even more refined Gaia DR2 parallaxes. They specifically looked at these potential iron core candidates again, including G8777.
yeah.
And with their improved analysis, using the absolute best DR2 data, they concluded that, no, the iron core idea didn't hold up for G87 after all.
Ah, okay. So better data resolved that particular puzzle.
It seems so, for that one anyway.
Oh.
It just shows how critical that measurement precision is and how interpretations can change as the data improves.
That's fascinating. What else did these big Gaia studies tell us? Any other major confirmations?
Yes, actually. That same Bergeron study from 2019 looked at the huge number of low-mass, relatively cool white dwarfs that Gaia found nearby.
Okay.
And by analyzing how these stars were distributed, their masses and radii, they found really strong evidence supporting the idea that their insides are, just as theory predicted, mostly carbon and oxygen.
So confirming the CO core composition for the most common type.
Exactly. I mean, everyone expected it based on how stars are thought to evolve, but
Yeah.
having this solid empirical confirmation from the actual population statistics,
Yeah.
that was something we didn't really have nailed down before Gaia.
So Gaia didn't just confirm the relationship between mass and size, it also helped confirm what they're made of empirically for most of them.
Precisely. The Gaia DR2 distances for the closest white dwarfs became so good, they basically weren't the main limiting factor anymore when calculating radii. It was a huge shift.
Okay, let's just recap this incredible journey then. We started way back with basic physics, quantum mechanics inside incredibly dense stars, leading to this fundamental prediction by Chandrasekhar and others.
Right, a prediction for how big these tiny dead stars should be based on their mass.
And then decades of struggle trying to actually test that prediction. Astronomers using clever tricks with light, gravity, orbits.
Pushing the limits of the tech they had, yeah. Finding hints, even intriguing possibilities like iron cores or strange matter, but never quite getting definitive proof across the board.
And then, bam, Gaia. Providing this unbelievable fire hose of precise data.
Just transformative, enabling these landmark achievements.
Like that first clean empirical test for a single isolated white dwarf, LRW37, using that amazing microlensing technique.
Yep, confirming the theory beautifully for that one star.
And then the large-scale confirmation from thousands of Gaia white dwarfs showing that, yes, the vast majority, that 73% number, behave exactly as the standard carbon-oxygen core models predict.
Confirming not just the mass-radius relation itself, but also providing solid empirical evidence for the expected CO composition of most of these common white dwarfs, absolutely the cooler, lower mass ones.
And having that confirmation is just, it's foundational, isn't it? That
Yeah.
means we can really trust using white dwarfs as tools.
Absolutely. It gives us much more confidence when we use them to measure distances, to figure out the ages of stars and parts of our galaxy, even probe fundamental physics. It shores up a lot of other astrophysics.
It really connects that weird quantum stuff inside the star to how we measure the whole cosmos. But even with Gaia basically saying, yep, theory's good for most, you still mention those earlier intriguing hints, right?
Hmm.
Those few objects that briefly looked like iron cores before the final DR2 data, and that historical chatter about strange dwarfs. They didn't pan out with current data, but the ideas were there.
Exactly. And while Gaia overwhelmingly confirms the standard picture, those historical questions, those brief moments where data seem to point elsewhere, they're a good reminder.
A reminder that science is always probing, always questioning.
Yeah. And the observations can always throw up surprises, things that make us double-check our theories, even the really established ones.
Which leaves us with a pretty cool thought to chew on, doesn't it? As we wrap up this deep dive, even when we get the most amazing data we've ever had, like from Gaia, and it confirms our main theories beautifully, what does it mean when even a few little outliers pop up, even briefly, that seem to challenge things?
Right. It suggests that even for these really common objects, these stellar embers scattered all across the galaxy, there might still be subtleties, maybe even surprises, left to uncover. Always more to learn.